Welcome to the ACOM seminar. First of all, I'd like to say that Lisa and John Ortega and I are the organizers, and we are looking for speakers for this fall. If you have visitors coming, please let one of us know. Today's speaker is Anja Schmidt, who's been visiting us for the last 4 or 5 weeks here. I first met Anja in 2011 at a conference in Hamburg where she talked about her recent PhD work on a 17th century, actually 18th century Icelandic eruption and the mortality it caused across Europe from the sulfate pollution. And I got to know her a year later at a conference in the Chapman Conference in Iceland, and it started a really good collaboration. This is her 3rd summer visiting us. She's now on a tenure track fellowship at the University of Leeds, where she also got her PhD in the UK. And she's an expert in volcanic hazards. She's been to Iceland many times in a helicopter over for this volcano, Hallrun, which erupted last year, was it? Yeah, 2014. And when she's not working on volcanoes, she's taking vacations to volcanoes in Japan. She's received a number of awards, including this year the William Smith Fund Award of the Geologic Society of London, and the Women of Achievement Award from the University of Leeds. Last year she received the George Walker Award for Volcanology, and she's also received the Springer Theses Publication Prize. And she's currently a scientific advisor to the UK Cabinet Office. So she'll be talking today about environmental effects of volcanic aerosol, past, present, and future. Anja.
Yeah, thank you. Can you hear me okay? Okay. So yeah, thanks for coming and listening to my research. I will mainly speak about Icelandic volcanic eruptions. And then for the last 10 or 15 minutes, I will also tell you a little bit of what I've done during the last 4 weeks. And I would also like to use the opportunity to thank ENCA and ACOM for giving me the opportunity to come here over the last 3 summers. I think it has been really fruitful. I learned a lot, and Mike is really a great host. And yeah, hopefully I can convince you that we've done some good science. And I also want to thank other collaborators, and a lot of them are actually here at ENCA, like Andrew, for example. So to begin with, I want to just give you a very brief overview of what I think where we are in the field of volcanic aerosol research and volcanic climate impacts. So in general, volcanoes emit a variety of gases and volatiles such as water vapor, carbon dioxide, and sulfur dioxide. And depending on magmatic composition, they also emit halogenated species. And if you have very explosive volcanic eruptions, like the 1991 eruption of Mount Pinatubo, for example, you can have a lot of volcanic ash. So volcanic ash is actually quite large in terms of particle size, so it falls out much quicker than, for example, sulfuric acid aerosol particles. So it's generally thought that the climatic impact from volcanic ash is really negligible. But it's an open area of research, so perhaps there's more to come here. And it's really the sulfur dioxide that's driving the climatic impacts of volcanic eruptions. Once it's in the atmosphere, it gets converted to form sulfuric acid vapor, and these vapors can nucleate to form new particles or condense onto existing particles. And once you have an aerosol layer in the stratosphere, or an increase in aerosol particles in the stratosphere or in the troposphere, these particles scatter incoming solar radiation back into space, and you end up with a cooling at the surface. However, sulfuric acid aerosol in the stratosphere actually absorbs long-wave radiation, so you end up with a heating in the stratosphere. And these processes are well observed, and we have a lot of observations of these, and it's well known. And this cooling at the surface and heating in the stratosphere then can also result in dynamical responses. You get a gradient between the stratosphere and the troposphere. So the observations indicate that following volcanic eruptions, you can have a winter warming. So that's warmer temperatures over the continents in Europe and North America for the first 1 or 2 years after volcanic eruption. What I want to point out here is that models actually don't do a good job reproducing this winter warming. And in general, it's really the direct forcing that has been studied the most in the past. What becomes apparent in the recent decade also is that if you use more complex climate models that include aerosol microphysical processes, such as coagulation, for example, and nucleation, to simulate a volcanic eruption, then you often get a much smaller temperature response as compared to a climate model simulation where you don't account for these processes. And I will come back to this later in the talk, but keep that in mind. So that's really also, to my mind, really an area of emerging research. So in general, there has been, in the last 3 decades also, a strong focus on stratospheric aerosol properties. And that's mainly because we had this eruption of Mount Pinatubo in 1991. This was a large magnitude eruption. And as volcanologists, we use what we call the volcanic explosivity index to indicate the magnitude of an eruption. So magnitude 6 is very large. And if you do a quick search on Web of Science, you see there are more than 500 publications that have the word Pinatubo either in the title or in the abstract. And if you look at recurrence frequencies, we expect one such eruption once every 50 years. So I guess what I'm trying to say here is that it's very likely that most of us will see another Pinatubo type magnitude eruption, okay? But it could be another 25 years or so before we have another opportunity to make these kind of observations and test our climate models. Yet there is this strong research focus, okay? So in the last, I would say, well, 10 years or so, there is a much more recognition of the role of, first of all, smaller magnitude volcanic eruptions that can be explosive. So these would be eruptions like Nepro, for example, in 2011. And this is a figure based on a paper published by Mike. But here you can see the volcanic aerosol column burden for June 2011. And you can see this column burden is basically made up from 3 volcanic eruptions, Grimsvötn, Nepro, and Kordenkoye. And all these eruptions were much smaller in magnitude in terms of their explosivity than Pinatubo. And the recurrence frequency for these eruptions is 1 eruption per year on average. So we have a much greater chance to make observations, for example, to simulate these eruptions in our climate models. But there are only about 50 papers or so. And not only is there more recognition of these smaller magnitude explosive eruptions, there are also other eruption types that we call effusive eruptions. So what I mean by these is these are eruptions that emit sulfur dioxide into the boundary layer or into the free troposphere. So the sulfur dioxide would not reach the stratosphere. There's not much explosivity. And often we refer to these as continuously degassing volcanoes, for example. Etna and Kilauea are good examples. They continuously emit SO2 into the free troposphere. And the point I want to make with this figure is that there are more and more satellite observations showing that these eruptions actually influence the microphysical properties of low-level clouds. So what you see here, this is a volcanic island in the South Atlantic Ocean, and this is low-level effusive volcanic activity. And you can see, this is a model satellite image, the clouds that are influenced by the volcanic SO2 emissions are much brighter than the surrounding marine clouds. And this is also reflected in the cloud droplet effective radius. So you can see it's much smaller in the area where you had the volcanic SO2 emissions. So that's well known as the first aerosol indirect effect. But I think what's less appreciated is that you really have to include these kind of emissions in your climate models if you want to understand, for example, the indirect forcing between pre-industrial and present day. And I won't go into too much detail, but if you're interested, there are a lot of papers here, and you can look at my own paper from 2012. So for today, I'm going to speak about Icelandic volcanism first, and mainly these effusive volcanic eruptions. That's one example here. That's the most recent eruption in Iceland. This is called the Holuhraun eruption. And we refer to these eruptions as flat lava eruptions, and I will explain to you why we call them this. And then for the second part, I'm going to speak about more explosive volcanic activity and volcanic aerosol properties and forcing of climate since 1990. So this is then really the part that reflects the work we've done here over the last 2 or 3 years. So when speaking about Icelandic volcanism, most of you might actually think about Eyjafjallajökull from 2010. So that was the eruption that no one can pronounce. Yeah. Anyway, so that was the eruption that caused a lot of chaos in terms of air traffic across the North Atlantic. And I want to put that in context. So what I show you here is the number of eruptions in Iceland in the past 1,150 years. And we know, based on these records, these are ice core records, written records, and so on, that there have been at least 205 historical eruptions. So the point I want to make here is, on average, we would see one eruption in Iceland every 5 to 6 years. That's a fairly high eruption frequency, okay? And that this is true. You see here, we had Hekla in 2000, Grímsvötn in 2004, then Eyjafjallajökull in 2010, Grímsvötn again, and now this most recent eruption at Holuhraun. And the one key message I want you to take away from this figure is actually most of these eruptions are explosive, so they would produce a volcanic ash cloud. So to volcanologists, Eyjafjallajökull was not a surprise, and it will happen again. It's very likely there will be another eruption producing a volcanic ash cloud, okay? But I'm going to talk about eruptions that mainly produce gases, okay? Mainly sulfur dioxide, and they have a slightly lower recurrence frequencies. The smaller ones occur about once every 40 years on average, and the larger ones, like Laki, once every 200 to 500 years. And in terms of, when I say flat lava eruption, in Iceland, a flat lava eruption is defined as an eruption that produces more than 1 cubic kilometer of lava. And you will see how much that really is in a second. So this is the most recent eruption in Iceland. It's referred to as the Holuhraun eruption. It started on 31st of August 2014, so on Wednesday it will be the 2-year anniversary of this eruption. And it lasted for 6 months until February 2015. Most of you might have heard about this as Badabunga eruption, so the journalists were quick adopting this name. And this is mainly because seismic activity, so this is the map of Iceland, and seismic activity started here in August 2014. And then the actual eruption actually took place in this ice-free part. So this is a big glacier here in Iceland, in this ice-free part between Badabunga volcano and Askja volcano. And the things I want you to note here is that it was quite fortunate that this eruption actually took place far away from any populated centers. The only problem was for us to get out there. That was then extremely difficult to try to reach the eruption site. But in terms of the air pollution that was created, that was really a lucky situation for the Icelanders. So a little bit about the eruption style. So in September, the eruption was at its peak. It was most powerful. We call this a so-called fissure eruption, and you have these lava fire fountains over here. They reached about 100 meters in height. You can see the volcanic plume here. There was literally no volcanic ash. Perhaps there was very little volcanic ash in the beginning, but this eruption was really dominated by gas release. And this plume reached up to 6 kilometers altitude, at times maybe a little bit higher, depending on the meteorological situation and the winds. And by the time we managed to get out there in January 2015, you can see that the style changed a little bit. So you don't have these vigorous lava fountaining events anymore. Instead, you have what we call a lava pond. But the point is there's still very strong degassing from this eruption. And this is several months into this eruption. And the eruption also produced some really, really spectacular lava flows, and still very strong degassing. So this is the lava flow field seen by a NASA satellite in January 2015. You see this is where it's still active and incandescent, and this will keep many generations of volcanologists really busy, because you can see very nice structures in this lava flow field, and this is really a landscape-forming eruption. So it's the largest eruption in Iceland in more than 200 years. It produced 1.5 cubic kilometer of lava, so remember, this is why we call it a flat lava eruption in Iceland. And to put that in context, you can cover Manhattan in 17 meters of lava. So it's really a lot of lava produced from these eruptions. But what really interested me the most is the amount of SO2 emitted. And there are a lot of lines of evidence that what I say here is true, so you must believe me. Basically, this eruption, yeah, I mean, sorry, I didn't say that very well. I'm saying there were, I don't have time to go into all the details, but there are ground-based measurements from the volcanologists and there are also remote sensing, ground-based remote sensing instruments that indicate that this is true. So this eruption emitted in early September about 120 kilotons a day of sulfur dioxide. And this is about 9 times the total amount that is emitted from the whole of Europe per day. So what I'm saying is that Iceland became this continental scale pollution source for several days. And I think it's fair to say we didn't really appreciate that when the eruption started. People were thinking this is an order of magnitude less. It took a couple of days for everyone, both atmospheric science community and volcanology community, to appreciate how much SO2 is coming out from Iceland. So the plume was also detected, and I will show you this by satellites and air quality monitoring sites, and I will show you results from that. And I think this eruption is exciting because there has been, in particular in Europe, a lot of focus on volcanic ash, so a lot of funding went into volcanic ash research, and rightly so, because it's the bigger hazard for aircraft, for example, has huge economic impacts. But this eruption is really, I think, an excellent test case for atmospheric models, for example, to test deposition schemes, chemistry schemes, to understand microphysics like nucleation of particles and volcanic plumes, and to understand climatic impacts from this eruption. And it has also implications. Also, I told you now this is a really big eruption. If we look back in the history of Iceland, we know there have been much bigger eruptions, right? So this is actually small in the grand scheme of things. So there can be much bigger eruptions from Iceland. So we need to better understand what these eruptions do to air quality, for example. So, and here are some first results. So what I show you here are hourly mean surface SO2 mass concentrations for September 2014. And these are measurements from air quality monitoring sites across Northern Europe and from Iceland. And the colors basically refer to the mass concentrations, and the different symbols refer to different observational periods. So first of all, if you look in Iceland, so in Iceland, these were really record high concentrations. They never measured such high concentrations. So in September, they exceeded like 2,000 micrograms per cubic meter. And this is well above the WHO 10-minute air quality standard, which is set at 500 micrograms per cubic meter. And this went on in Iceland for almost 6 months. On and off, they had transient pollution events, and people were asked to stay indoors, don't do any outdoor activities, and things like this. But what's also exciting is that there were, for example, measurements made in Ireland on 6th of September, so a couple of days into the eruption, where SO2 mass concentrations exceeded 500 micrograms per cubic meter for a couple of hours. And these are really record high concentrations measured in Europe since the 1980s. And there are also other measurements in Austria, for example, that confirm that the SO2 was transported really quickly into Austria. So these are distances of more than 2,700 kilometers. And I personally think it's the best case we have in terms of observations for long-range transport of volcanic pollutants. And I haven't looked into details, but lots of people start now looking at the aerosol measurements at the same sites. So I think there's a lot more we can do here. This is just a snapshot of the satellite data. The point I want to make here is that both UV and infrared satellite instruments actually detected this volcanic plume. And I want to remind you, this plume is at very low altitude at times, and we are talking about high northern latitudes. So this is not trivial for satellite instruments. And here I show you an example where I just compare the vertical column densities that, as retrieved by OMI in the top panel and Ayasi in the bottom panel on 5th of September. So that's one day before this air pollution episode in Ireland. And the point here is really that both instruments detect this plume in a similar location, but the magnitude of the detected or retrieved column densities is quite different. And I think for those interested in satellite retrievals, again, more work could be done here to understand why these retrievals are different and how we can improve this. And Ayasi can actually also be used to retrieve plume heights. So this then in turn could allow us to drive, for example, climate models with these inputs. So when this eruption started, that was actually my first summer here, and I met Andrew for the first time, and we spoke at the time, and Andrew was very quick in believing how much SO2 came out of this eruption, and he set up a CSM to, basically our interest was like, if there's so much SO2 emitted, is there any potential impact on regional climate in the North Atlantic from this eruption? So here I show you results, both showing you the forcing of climate for the autumn and winter months as compared to the forcing of climate over the summer months. And you can see in winter, really, there's not a strong forcing from this eruption. And this is mainly due to the lack of incoming solar radiation at these latitudes. But if this eruption had continued into the summer, then according at least to CSM, there would have been quite a strong forcing from this eruption. And the point is, this forcing is actually dominated by the indirect aerosol forcing. And just to give you some context, this forcing would have exceeded or could have exceeded that from current anthropogenic sources over the same region. So that's quite a significant forcing. Unfortunately, the eruption stopped in February 2015. So yeah, I say this, but I think, so we never had the opportunity to really get to this point. But the point, I guess, we tried to make in this paper was also about, for example, aerosol optical depth measurements and trying to get in situ measurements. So there was no aircraft flown from any European research university to try to sample the plume. And there are now also more work is now being done on looking, for example, at the changes in effective radius from this eruption. So what I show you here on the top panel are modest satellite observations of the effective radius changes for September 2014 and October 2014 compared to the 10-year climatology. And this is work by Jim Haywood that's currently under review. And you can see there's some significant changes in cloud effective radius due to this eruption, both in September and October. And using the UK model, this is HAGEM 3, I suppose that's comparable to CESM. You can see that the model predicts similar magnitude changes. In particular, October is doing a good job in terms of effective radius and also similar locations. That's not quite true for September. And the point here is this really, we can test how well the skill of our models in terms of simulating the first aerosol indirect effect. And we have observations, and I think it's a really nice natural test case to do that. So now I want to talk about an eruption that was an order of magnitude bigger. It's the so-called Laki eruption. Laki erupted in 1783, and it lasted for 8 months. You can see, so remember, Holochurn produced about 1.5 cubic kilometers of lava. Laki produced an order of magnitude more lava. And it emitted about 120 teragrams of SO2. That's the same amount as all man-made SO2 emissions globally per year. So again, a significant amount of SO2. The difference to Holochurn is that Laki actually had some explosive phases, and they are depicted by these red clouds down here. So you can see the eruption was most vigorous at the start. And basically, during these more explosive phases, the SO2 was emitted into altitudes between 9 and 13 kilometers. So that's the upper troposphere, lower stratosphere above Iceland. Yeah, and this is actually in the background, you see a picture of what it looks like, what Laki looks like now. So if you ever have a chance to go to Iceland, I highly recommend you go there. It's a really spectacular site. So I think you will enjoy looking at that. And what's really nice about Laki is that there are a lot of historical records of this eruption, both from Iceland, but also across the whole Northern Hemisphere. So what I show you here, this is a compilation by Thor Thordarson and Steve Self, who looked through historical records across the Northern Hemisphere and noted that people actually described what they called a dry fog or a haze during the summer of 1783. And here you see the extent of these observations and also the occurrence or the first appearance of this haze. And of course, at the time, people didn't link that to an eruption in Iceland because they didn't know there was an eruption going on. Although I should say Benjamin Franklin was in England at the time, and he was actually, I think, one of the first to link what happens in the atmosphere, what he saw in the atmosphere, this fog he saw in the atmosphere, to volcanism in Iceland. He had the volcano wrong, but it's still quite impressive. So this is probably the birth of volcanic atmosphere research in a sense. So Laki was likely the biggest atmospheric pollution event in historic times. And there are also other records. So this is a guy, he was like 19 years old from the Netherlands. The eruption started in June, and he wrote a paper in July describing what he basically observed in his surroundings. So the first thing he noted is that people who had asthma actually experienced new asthma attacks during the summer of 1783. And he also described that the leaves on the trees had withered, and in the middle of June, things looked like if it were October or November. So basically something was going on there. There are these historical records and these descriptions, but it's very difficult to really link that back for sure to this eruption in Iceland. Every school kid in Iceland learns about Laki because it had a devastating impact on Iceland. 21% of the population died, mainly due to starvation, and 75% of the livestock perished. But the impact wasn't confined to Iceland. There are records from England, for example, mortality records, that show that in summer 1783, mortality was 10 to 20% above the 50-year moving mean. And this is depicted in this figure. Basically, there's a spike in summer mortality in 1783. And it's very unusual that people actually die in summer at that time, because normally that's the time of plenty. You just have your harvest in. So, and similar accounts are also found in France, the Netherlands, Italy, and Sweden. And here I just want to, there's a book, basically in Iceland there was a priest who observed the eruption, and he wrote a diary. And this book now has been translated into English now. So if you're interested in that, it's a really nice bedtime, but it's a quite interesting bedtime read, trying to understand how people in 1783 dealt with an eruption of this size. And actually Jørgen Steinkrimsen uses some terminology that we still use in volcanology now. So you can order that on Amazon if you want. And as I said before, and it's not easy to, if you just go back for a second, it's not really easy to link this increase in mortality to the events in 1783. And this is actually what I tried to do initially during my PhD, but I never managed. I kind of failed utterly trying to do this. So I changed approach and thought, like, what would actually happen if we had such an eruption nowadays? And I want to remind you, the recurrence frequency is one eruption every 200 to 500 years. So that's a low probability event, okay? But it can happen. So the way I did this, I used a global aerosol model that is developed in Leeds. It's called GLOMAP. It's very similar to WACAM-MAM. And I simulated the eruption under present-day conditions using the eruption source parameters as I knew them from the 1783 eruption. So I emit sulfur dioxide, and then the model has a chemistry scheme to convert to sulfate aerosol. And then the model can track not only the mass of particles, but also their size. So this allows me then to assess how this eruption could impact air quality. And my air pollution metric is PM2.5. And I get this from the model. And then I can apply epidemiological evidence to calculate the potential impacts on human health. And here I do the same as the EPA would do. It's standard methodology. You look at your change in PM2.5 concentrations and then calculate the potential impact on premature mortality. So the first thing I want to show you here is a time series of daily mean surface PM2.5 mass concentrations as simulated in the model. So this gray shading here are the control simulations, and you can see in the model these are European mean concentrations. They are about 20 micrograms per cubic meter in the summer months, and then slightly lower during the winter months. And if you then look at the simulation where I included the Laki eruption, you can see throughout the summer months, these European daily mean PM2.5 concentration exceed 25 micrograms per cubic meter. And that's a key metric because it's the air quality standard set by the WHO. And just to give you a feeling, so what would the world actually look like if we had transient episodes of volcanic air pollution reaching, for example, Europe? So we had an air pollution event, nothing to do with a volcano, okay? In Yorkshire, where I work now in the UK in April 2011. And this is on a clean day, so we have about 15 micrograms per cubic meter on average. and you can see several tens of kilometers inland. And if you have 45, during this air pollution event, we had about 45 micrograms per cubic meter, which is similar to that change I just showed you from my model simulations. And you can see visibility is drastically reduced, actually. And of course, visibility is also dependent on humidity, so that's not a perfect comparison. But the point I want to make here is really that people would probably notice that something is going on. So that has implications for governments, how they would communicate about these kind of events. And then now that we have assessed this change in PM2.5 concentrations due to this eruption, we can apply epidemiological evidence to calculate the potential increase in mortality due to this eruption. So I combine the simulated impact on air quality with population data and baseline fatalities, and then so-called concentration response functions. So these link a change in PM2.5 concentrations to a change in the health risk. And this is basically what we calculated. So here I show you mortality due to cardiopulmonary increase in cardiopulmonary deaths in the year after the onset of such a Larky-type eruption. And if you look at the total, so I only calculate that at the time for Europe, we calculate, depending on the length of exposure, there could be up to 140,000 additional fatalities. And this is a significant number. It exceeds annual mortality from seasonal flu. And to give you more context, globally, about 3.7 million premature deaths occur due to outdoor air pollution. The other thing I want to point out, although this study is not about reproducing any historical records, it's quite astonishing that basically we see high mortality rates in similar countries as where we had these historical records of high mortality rates. And the number of fatalities is basically a function of pollutant transport and population density in these locations. So I want to summarize this first part. So this was mainly about effusive volcanic eruptions in Iceland. And I've shown you that even these smaller volcanic eruptions like Holuhraun can have significant effects on air quality. So for Holuhraun, the effects were very short-lived in the far field, so that's about 1,000 kilometers away from the volcano. And there were no health effects there, but in Iceland, air quality was actually badly degraded for about 6 months, and there's still research ongoing now to really understand what happened. So I know the number of asthma inhaler sales went up, for example, during the first 2 months. And if you had a bigger eruption, like a Larky-type eruption, which has a lower recurrence frequency than Holuhraun, for example, then this eruption could actually degrade air quality for much longer, potentially for weeks to months, which in turn could then have significant effects on human health across Europe. So I also want to make a point about continuously degassing volcanoes. I think these kind of eruptions really give us a nice opportunity to quantify aerosol cloud radiation interactions. This is the biggest uncertainty in climate modeling, for example, and ever since the first IPCC report, we didn't really reduce this uncertainty. So maybe these kind of natural test cases would be a good opportunity to do that. And I know that Andrew is very active in that area and interested in going to Hawaii to use Kilauea as a test case. So these volcanic plumes could be used to better understand particle formation, growth rates, removal rates. Yes, and also, as I said before, and what kind of impacts they have on air quality. So now I want to talk about the work we've been doing in the last 3 years, actually. So basically what I show you here is a plot from a paper by Anja Schmidt published in 2014. And here I show you global mean temperature anomalies from 1990 onwards. And I know the plot is very busy. If you first focus on the red lines, these are the observations of temperature change. Okay? And then if you look at the temperature anomalies predicted by CMIP5 model simulations, these are the blue lines here. You can see there's quite a large discrepancy between the temperature anomaly predicted by CMIP5 model simulations compared to the observed temperature anomalies. And this has received a lot of attention in the last couple of years. It's known as the hiatus, or this apparent change in the rate of global warming. It's a slowdown in the rate of global warming. And the point that Gavin made in this paper is if you actually, the point is that these CMIP5 models were prescribed volcanic forcing fields. So they used aerosol optical depth measurements from satellites, and they assigned a certain effective radius. And these data sets came from Sato et al. And the main point is that after the year 2005, in the Sato data set, they assume there are no volcanic eruptions. Okay, so the AOD goes back to stratospheric background values. And now in this paper, Gavin Schmidt basically pointed out if you updated the volcanic forcing data set, as shown here, so these are the differences to the original data set. So he decreases the forcing for Pinatubo. I won't go into this for now, it's not so important. And increases the forcing since 1998 for volcanic eruptions. And he also makes changes to the solar forcing and the tropospheric aerosol forcing. And then if you repeated your model simulations, you would end up with this black line. And the point is, you can see these model simulations get much closer to the observed temperature changes. So there's an indication that really the volcanic forcing is very important to include it and to update it. There were volcanic eruptions since 1989 that we need to include. And the way this is done in this model is basically by using satellite observed aerosol optical depths to force the model. And I want to ask the question, how good is that? So how good is this forcing field? And a way of doing that is the first thing we can do is we can actually, instead of prescribing aerosol optical depths in models, we could try to use actually SO2 emissions, so the precursor gas, and let the models calculate the aerosol forcing fields themselves. And this is possible because we can now actually compile volcanic SO2 emission databases. First of all, volcanic eruptions are increasingly well reported and characterized. So we have geophysical observations, we have satellite observations. And this is one of the databases I compiled. So what I show you here, these are volcanic eruptions since 1990 as a function of latitude. And the size of the circle indicates the magnitude of their explosivity. And these are all eruptions that have been reported since 1990. And now I overplot in colors those eruptions where we have information on the amount of SO2 emitted. And these are the ones, the colored ones, are the ones we are going to take into a climate model. And I just want to give you some feeling for the numbers. So in 1990, if you look from 1990 to 1999, there was about 22 teragrams of SO2 emitted from volcanic eruptions. And that was, of course, dominated by Pinatubo. So it would only be 5 teragrams without Pinatubo. There's a discussion about how much SO2 Pinatubo exactly emitted. 2000 to 2009, about 8.5 teragrams of SO2. And if you look at 2010 to 2015, so that's only halfway through the decade, okay, we are already at 9 teragrams of SO2. And I didn't even include this eruption at Holochrön, which emitted another 10 teragrams of SO2.
What's the definition of this VEI?
Yeah, okay. So this is volcanic explosivity index. So the larger the number, the more explosive this eruption was. So for example, Pinatubo was a VEI 6 in 1991. And you can use it roughly as a measure of how high the SO2 reaches into the stratosphere because the eruption is more powerful. Okay?
Like a logarithmic scale or a linear scale?
Yeah, it's a log scale. Yeah. 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 So yeah, it's like the Richter scale, but for volcanology. It's not perfect, but yeah. Okay. So, and this is having this SO2 emission database, we can basically exploit new modeling capabilities, and this is work done here at ENCA and published by Mike Mills. So we basically use this SO2 emission database in CESM WACAM, which has a prognostic stratospheric aerosol scheme. So again, the point is you go from the SO2 gas to calculate the aerosol and the optical properties, for example. And if you want to know more about this, then you can go to Mike's paper. And one plot I want to show from this paper is actually that the model is actually doing a very good job compared to, for example, LiDAR observations. So what I show you here is stratospheric aerosol optical depths in the visible, so that's at 525 nanometers since 1990. And the black line is the model simulated stratospheric aerosol optical depths at mid-latitudes in the northern hemisphere. And you can see for this large explosive volcanic eruption from Pinatubo, the model agrees very well with LiDAR measurements from Geestach, and also in the later period where we have these more smaller magnitude volcanic eruptions, you can see there's very good agreement with LiDAR measurements. So we can trust that the model is doing a good job going from SO2 emissions to calculating aerosol optical properties, for example. Another point I want to make here is models like CMIP5 models, they would often use a prescribed forcing field, as I explained to you before. And you can see, for example, compared to the CCMI recommendation, there's quite large discrepancies during the Pinatubo period, but also during this period where we had an increased frequency of these smaller magnitude volcanic eruptions. So now that we looked at the optical properties, I was interested in understanding, okay, what does this do in terms of the forcing of climate? And here I show you the global mean volcanic forcing over time. And you can see during Pinatubo, we have this peak forcing of about -3 watts per square meter, which is in really good agreement with previous studies, and it's also in good agreement with, for example, ERBI radiation measurements. And the one point I want to make here is that remember that these CMIP5 models assume there's no volcanic activity after 1998, and that means they get no forcing from volcanoes. And you can see here in this model, you see quite a strong forcing after 2005. It at times reaches -0.5 watts per square meter. So you really need to include an account for these small to moderate magnitude volcanic eruptions if you want to get your forcing of climate right. And what we can do as well is we can basically decompose this forcing and look at the different components like the aerosol direct forcing and the aerosol indirect forcing. So here the aerosol radiation interactions or the direct forcing is shown in the blue line. And what I find exciting in this model is really that there's quite a strong aerosol cloud interaction forcing that is positive. And what's interesting is that even though Pinatubo was of much larger magnitude, okay, emitted much more SO2 than compared to the eruptions in 2008 and 2010, this cloud forcing is actually of similar magnitude. And I'm currently looking into this. So we're saying this is due to changes in the number of ice crystals in the upper troposphere and their size. So I'm diagnosing this and trying to understand what is causing this change in forcing. So, and lastly, I wanted to try to, if you remember this plot I showed you from Anja Schmidt with the CMIP5 models and the observations, I wanted to try to understand how this updated forcing from our CSM simulations translates into global mean temperature change. So what I show you here are, again, is a temperature anomaly over time. And these are the observations. So these are Hartkrut-4 observations. And I removed ENSO. So I did a regression and then removed ENSO. And then I used the Sato forcing that was used in these CMIP5 simulations, put them into an energy balance model, and calculated the temperature change. And you can see is that at the point where you can basically see there's a large discrepancy between the temperatures predicted if you use the Sato forcing and the observed temperatures. So this blue line now shows this updated forcing by Anja Schmidt. And remember, he used satellite-based AOD observations. And you can see, indeed, as he predicted, as in his paper, the discrepancy is less. And it can actually explain a third or more of this difference between observed and model simulated temperature changes. So now, the red lines and the shading, these are our model simulations. This is a completely different approach. We went from SO2 emissions, and we find a very, very similar change in global mean temperature. So I think that's a great result, and it's nice that coming from two different, using two different methodologies coming to a similar conclusion. And the main point is really you must include these volcanic emissions or the volcanic forcing in your models if you want to predict temperature changes. So now then, to make things even more complicated, let's think about the next decade. So my understanding is that in all these RCP scenarios, there's no they don't account for any volcanic forcing. And I understand this is of course difficult because we can't really predict volcanic eruptions. But I still want to try to make a point. If from 2015 onwards, we assume no volcanic forcing, this is the predicted evolution of the temperature, okay? If your model used Sato and you continue to use the Sato forcing, i.e. no volcanic forcing basically, you see you are, again, far away from even those models that used some volcanic forcing, like this updated CMIP5 forcing and our own forcing. And then what's interesting perhaps is, so what I did is I did something very simple. I just applied the same forcing as 2006 to 2015 and 1990 to 1999, that's this one. So if you had another big Pinatubo magnitude eruption, you can see there's quite a big drop in temperatures. So I think that has implications for decadal predictions of climate change, for example, and maybe at some point we need to think about how we implement volcanic forcing into these kind of forecasting systems, for example. And that's my summary. So I've shown you some results. So this is a paper led by Mike Mills and published in JGR, where we use CSM WACAM with a volcanic SO2 emission database from 1990. And we show that the output from this model actually agrees much better with both in situ and ground-based measurements than the standard observations from CCMI, for example. And the model does a really, really good job reproducing observations. And currently, I've shown you work where we diagnose the volcanic forcing, and there's more work to do here. I think we can distinguish between the direct aerosol effects and the indirect aerosol effects. And you really ought to update old CMIP5 volcanic forcing data sets in all models that are used, and it has implications for CMIP6, I think. And I'm also, and I haven't talked about this, I'm also interested in looking, I started that already, I look into volcanic eruption frequencies in context with these hiatus and surge periods before 1990, for example. And that's it for me. Thank you very much for listening.
Do we have questions? Yeah.
So what is the recovery time for an eruption like Pinatubo, or when the atmosphere, or the time that it takes the atmosphere to come back to quasi-normal?
Yeah, so it's about 3 to 4 years for Pinatubo, and it's much shorter for, I think this is a nice plot to see it. Yeah, so this is the peak forcing. So the eruption started in June 1991, and I would argue, by 1990, end of 1995, we are back. There have been some other eruptions that make that difficult, but yes.
So I guess the more intense the eruption, the longer the recovery time?
Not necessarily. So this is where these aerosol microphysical processes come into play. So if you have, the more SO2 you emit, the less efficient, first of all, your chemical conversion to sulfate becomes. But then also these particles grow to very, very large sizes, and then they fall out faster. And that has been shown in 1989 by Joe Pinto. So there's no linear scaling between the magnitude of an eruption and its temperature impact, if you account for microphysics.
I have a question to this plot. For these, for the Pinatubo, most of the aerosol went, or the SO2 went into the stratosphere, and some fraction stayed in the troposphere. And for the other volcanoes, what is the fraction? Because I wonder why maybe that much more stayed in the troposphere, and that's why you get less of the forcing, but more of the cloud effect. Maybe.
Yeah, exactly. So this is exactly the case. So you see Pinatubo is dominated by the direct forcing, right? Because the majority of the mass was emitted into the stratosphere. Whereas these later eruptions are indeed less powerful, therefore they reach perhaps the upper troposphere and lower stratosphere, and they have a much greater potential to impact clouds. Yeah. But I think it was still surprising to similar magnitude. Yeah.
Can you go back to your last hiatus figure there? Yeah.
With the future?
Yeah,
Yeah.
that's fine. So it still seems like that we can't represent the observed change.
Yeah, sorry, I forgot to say that properly. Okay, so maybe I go back to Gavin's figure. So the point was that Gavin also updated, remember, the solar forcing and the tropospheric aerosol forcing. So that's something this is work in progress, really. I think if in my energy balance model, if I added these updates, perhaps I would go, not perhaps, I think I'm fairly confident I would come with this red line, would probably come a bit closer.
Okay.
And then there are other difficulties. This is really a simple energy balance model, right? So it's not, I would be surprised if it perfectly reproduced the observations. But this is basically what the IPCC would be using.
Okay.
So I think other forcings are potentially underestimated.
So in the early part, you mentioned halogens as potentially being released. Would there be any air quality impacts associated with those halogens?
So it's discussed rather controversially. The only semi-qualified answer I can give comes from work in Iceland. So locally, it's a big hazard. So fluorosis is a big problem in Iceland after volcanic eruptions for sheep, for example. I have yet to see any observations of transport, for example, from Holocene of large amounts of halogens into Europe. So I think they are washed out before they can. There's no long-range transport of halogens at this altitude. But I think it's a controversial topic, and I'm not the expert on halogens.
What about hydrogen sulfide?
Yeah, so for Holocene, there's a paper saying they smelled hydrogen sulfide in Sweden, I think. And people after EF-verdrückte, people in the UK claimed they smelled hydrogen sulfide. So this is believable, even though it oxidizes fairly quickly.
At the same plot, is there a reason why the red line is since it matches better in the end, but it doesn't seem to match at Pinatubo anymore?
Okay, good question.
I mean, what's the uncertainty bar, or this shading? What does it represent?
So the shading is just a change in the climate feedback parameter. So it could be that volcanic eruptions or the forcing from volcanic eruption has a different climate sensitivity than other forces. Okay, but to answer your question, and it's a good spot. So if I don't think I have this plot, but basically if I changed the mixed layer depths in the energy balance model, I make it lower for Pinatubo because it was a bigger kick to the system. This goes down here, so it matches the observations better. But there's also something to be said that this old Zeto forcing in this case seems to actually match better with the observed temperature change. And Gavin argued in his paper, he argued that the Pinatubo forcing has to be reduced instead of. So the point is, I think it's not. I don't want it to be the focus of my paper, but I think something has to be done there. We can't even get Pinatubo right.
I thought CSM was doing all right, but maybe I remembered incorrectly. Yeah.
Okay, so let me stress one more time. So I'm just taking the forcing calculated in CSM, and I think I haven't overplotted observations yet, but this is a good forcing. This is not out of the... and I take this and put that into an energy balance model. So the temperature anomaly is not calculated based on, say, free running simulations in CSM. We need to keep that in mind, I think. Thanks.
I would just add, CESM1 had too much cooling after Pinatubo. And I think you may be onto something with the mixed layer of the ocean. In this model, you're using about 100 meters.
So this it's a standard what the IPCC would assume 100-meter mixed layer, and I reduced it to 35. Let me see whether I have the plot. Maybe I can convince you. Sorry.
But the top 10 meters or so could have a bigger temperature change.
No, I don't have it, I'm afraid. Yeah. But I can show it to you, Flavio, if you want.
Any more questions? All right, let's thank Anja once again. Thanks.